Good morning. Today we're going to talk about correlation of FE results and test data. And actually the presentation is going to start out looking at the DesignLife virtual strain gauge, its capability. I'll walk through a brief demonstration of how you would use the virtual strain gauge. We'll talk about how to take that information and use it with test data to correlate with test data. I'll then look at the Lodz Reconstruction process, which is a worked example inside of DesignLife 9, and show how to use that to take measured strain data and to reconstruct the loads that would have resulted in those strains. And I'll give you a demonstration of that as well, and then we can open up for questions. HBM nCode currently actually has 3 products today, software products. One is GlyphWorks. GlyphWorks looks at measured data, and again, this would actually probably be the tool that may have been the source from some of the data we do correlation with. Automation is a web-based data management tool, again, for measured data. And then finally, we're going to focus on DesignLife. DesignLife is a tool that uses FE results to do an upfront fatigue prediction. However, you'll see in the presentation today that it has a pretty extensive capability for doing signal processing and, again, correlating with tests using the virtual strain gauge. From the point of view of a user, one has 2 paths for going off and trying to predict fatigue. One could be using measured data, applying strain gauges, recording measured strains, and using those in a fatigue prediction route. The second is using DesignLife along with FE results to go off and do a virtual fatigue prediction. And again, they both have benefits and detractors. And typically you'll find that a combination will be used in most design environments. Most likely DesignLife upfront for initial design, but eventually at the validation stage, most likely there'll be some test data taken. We're going to focus today on a capability inside DesignLife called the virtual strain gauge. And what this is the ability for a user to lay strain gauges on his FE model the same way that you'd lay actual gauges on a physical part. And then there is an engine, a virtual strain gauge engine, that will take those markers, take the load provider, however you're describing loads into DesignLife, and here a load provider matches up measured load histories or constant amplitude applications, or maybe a transient, along with FE results to synthesize a stress history for fatigue. Here the stress history is going to be interrogated by the virtual strain gauge, and each leg of the gauge will output a signal of stress or strain depending on your requests. The virtual strain gauge actually has 2 components to it. One is the definition of gauges inside of the FE input glyph. See that in just a second. And then the second is the actual engine itself that takes that information in terms of locations of gauges and outputs the strain histories. The actual controls inside the FE input glyph for the virtual strain gauge give me the capability of specifying multiple gauges, gauge types, and gauge types here could be things such as just standard single gauge, T's, some sort of rosette, either delta or rectangular. It then gives me the ability to place that onto the FE model, and that would be at either a surface node location or for shells at an element centroid. If we're dealing with shells, we have the capability of specifying which surface of the shell we're going to recover, or both. And we also have controls to allow us to orient the gauge. The gauge is going to be placed on the surface, and so we know what plane it is in, but we have to orient the legs. And so there are capabilities for me to go in and specify the orientation in terms of geometry of the model, either a vector or points of nodes, or I can put it in by eye with an angle, and I'll show you that in just a second. The goal of the virtual strain gauge is, again, to allow me to take my FE model and output strain histories that would mimic what I would be able to measure in the field or in the test lab. And so these strain histories can be brought in, and they can be physically overlaid with the actual measured strains. The goal here, if I cannot get an accurate stress or strain history represented for my FE model, I can never get accurate fatigue results. So this is a preliminary step for me to go in and to correlate my model prior to the fatigue calculation. With that, let me open up DesignLife here. I've opened up DesignLife, and what you're looking at is the DesignLife interface. And for this particular demonstration, I'm going to start from scratch and actually build a process for the virtual strain gauge. Here I have two inputs. One input is an FE model that has 3 load cases, and we'll look at that in just a second. And then the second input is a series of force histories that will be applied to the individual loads in that FE model. I'm then going to pass that information into the solver glyph, which will be a virtual strain gauge. So I'm going to go to the DesignLife palette and generate the virtual strain gauge solver. Then we'll look at this data in 2 different ways. One, I'm going to display it directly, just the strains coming out of the legs of the strain gauge. We'll use that display for that. But I'm also going to take the same information and I'm going to pass it into another glyph that's going to actually allow us to take the individual legs of the rosette and compute from that things such as stress invariance, von Mises principles, max shear. And that particular glyph is called the Strain Rosette. So once I have the individual glyphs arranged, I need to develop the data paths, and to do that, we build pipes between them. So I'm just going to go in and define the data paths that I'm going to use. And what I have here now is the complete process that I'm going to use. So let's go off and look at our inputs. The first input is the FE model. What this is a an attachment to a disk, a farm implement, where I have the upper portion of this spring mounted to the frame, and the lower portion, the bracket, actually mounts to the disk itself. And in this particular model, we have 3 load cases applied, one fore aft, or in the X direction, one lateral in the Y, and one vertical in the Z. And we can actually go in and interrogate those stresses inside of the FE input glyph. Let's just go and grab the last one, the Z stresses. So I have those 3 stress states, and now what I want to do is I want to go in and apply a gauge to this model. And so when I have the input glyph highlighted, we have a toolbar at the top that is displayed, and the last icon in that toolbar brings up the virtual strain gauge manager. This particular data form allows me to go in and import existing gauges or take existing gauges and edit them. I'm going to come down here and I'm going to ask to add a new gauge. So it brings up the data form we saw earlier. And here I can specify names for the gauges. I can specify the type of gauge that I want. Again, a single leg, a T, a rosette. We'll do a rosette. I have the ability to specify the location where I want to place this. And so, again, this could either be element centroids or nodes. We'll go to nodes. And then I could key in a node ID. I could go over, key in a coordinate location to have it snap to the closest node, or I could just pick it with the cursor, which is what I'm going to do. And so first, I'm going to zoom up onto the inner radius where I want to actually place the gauge. And you can see that the nodes highlight where I step on a node, so I'm going to go in, select that particular node. Down below, if these were shells, I could control what surface I was looking at, or both surfaces. I have controls below that to specify how I orient the gauge. And so I could place these either geometrically, and at times that may be how they're described to you. And that geometric location could be just a vector in space. It could be selecting nodes on the model to orient the part. Or I can take the default, which I'm going to do, zoom up here and look at the gauge. And a final orientation capability is just to go off and specify an angle I want the gauge at. So I can control the in-plane position. Leg 1 will be the leg that actually has the different colors. So the gold leg is going to be the specification of leg 1 when we see results coming downstream. Again, I could create as many rosettes on this, or actually any style gauge as I want on this part. I'm going to leave it at the single gauge here. So this is an input that's going to specify to the solver where I want to extract strains. Solver self to virtual strain gauge solver, I need to do several things. One, I have 3 load cases in my FE model, and I'm going to pair those up with 3 sets of applied load histories. A load history in the X, the Y, and the Z. And that's done with load mapping. Load mapping is the facility inside of DesignLife that allows me to go in and to take FE results and turn those into a history of stress or strain for the fatigue analysis, or in this case for the virtual strain gauge. And here in the upper left-hand corner, I have the 3 load cases coming out of my final element results. Down below, I have the 3 measured load histories coming in, and they've been paired up automatically, just one-to-one by the software. But I have the ability to go in and to control how they're paired up if I like. I'll leave them automatically paired because that's appropriate for this particular model. Secondly, I need to assign material properties. In this case, the material properties are here solely to give me elastic constants. I need to have Young's modulus and Poisson's ratio available so I could jump between stress and strain if I need to. So all I really need to do is find a material in the database that's the proper alloy. So I'm going to come down here and find the first steel that I find and just apply it to my model. Again, all it's going to be interested here is Young's modulus and Poisson's ratio. We're not going to use the fatigue properties at all. Then finally, the last thing that we have are some properties that control the input and the output of the virtual strain gauge solver. You'll see in the center section here, it specifies what I'm reading in from my final element results, and this could be stresses or strains. It's specification of where we're getting the strain gauge information from, and metadata means we're reading it in from the virtual FE input glyph. We have units of both strains and or stresses that I would be inputting, and here I do have to make a change. My FE model is in pascals, so I'm going to switch the input to pascals. And then the lower section specifies what is going to be output to the system. I have the option of either stresses, strains, or both. I'm just going to do strains. And again, I can specify the units that will be output. We'll just leave it at microstrain. The last process here the load provider that we bring in could be a duty cycle, as well as just a single load provider such as time series or time step. And so if it is a duty cycle, there is a control that says how we deal with the duty cycle in terms of sequencing the events. With that, I have everything specified, and so I'm going to come up here, run the process. Again, it's relatively quick since we're looking at a single location. The first output we had here were the strains from each leg of that rosette. And so we're looking at the microstrain output from leg 1, leg 2, and leg 3 of that rosette. And again, these were computed from the superposition of the static stresses from the individual unit load cases being modified by the input load histories. So leg 1 is really the combination of the strains in that direction from load case 1, load case 2, load case 3, each one of those scaled by their appropriate load histories. The other glyph that was in this flow that I created was called the Strain Rosette. And this actually has the ability to bring in one or more rosettes. And these could be either real gauges that were measured in the field or the virtual strain gauges that we're calculating from DesignLife. And from that information, compute invariance, principles, von Mises, directions to the first principle. It can even do critical plane calculations. And so what it did was bring in the results from that one rosette, and it's outputting here things such as min and max principles, max shear. I have basically both stress and strain computed here for all the invariants. Again, that would be very powerful if I wanted to take a measured strain gauge and go off and do a fatigue prediction on it, because here I could actually calculate a NAVS max principle calculation or a critical plane direction and do fatigue calculation on it. But again, I can also use this information to go in and to look at my virtual strain gauges and start to decide an ideal direction to apply a real gauge. What is the direction of the max principal stress? Okay. With that, let's go back to the PowerPoint. And talk a little bit about things you could do for correlation. Again, with the virtual strain gauge, we can output one or more legs of measured, well, simulated strain. One thing we could do is bring in the measured strain along with that and plot those simultaneously together. And within the nCode interface, our display capability allows us to go off and look at that in several different ways. So here I have 3 XY displays on the right-hand side. Each of them are displaying both the virtual strain history along with the measured strain history that's coming in from below. And at the top, I've just plotted them one over the other to do a visual correlation. Below that, I've taken the same sort of display, but I overlaid one on top of the other, so we can look at differences between those. And then on the bottom display, I've actually cross-plotted the virtual with the measured. This cross-plot can actually be used not only to cross-plot things such as 2 strain histories, but almost any signals that you bring in with a virtual output. And so things such as looking at strain response versus acceleration to try to decide whether or not I have a correlation between the two and whether I need to look at my model in terms of dynamics versus quasi-static. So just within the display capability, you have a great deal of capability to go off and compare items. In addition, DesignLife comes with a glyph palette that's called Digital Signal Processing. This is just standard DesignLife. And in here are a whole series of tools that allow you to do basic signal processing on either your input measured data or things such as your output virtual strain gauges. I'm just going to go off and just point to just a couple here. But in here you have filters that you could go in and filter the frequency content of an input or output history to low pass, band pass, or high pass, that to include or exclude frequency ranges. In terms of looking at the actual frequency content, there's another glyph called Frequency Spectrum that'll bring in a time history and output an amplitude or power spectral density. So I can look at the frequency content of my time histories. Again, I may be trying to make decisions on whether I need to look at my model in terms of dynamics, or I can get away with quasi-statics. There's statistic glyphs here, both overall as well as running statistics. A running statistics glyph would take an input or a output time history and give you statistics on it, things like averages, maxes, mins, over a averaged portion. So I can look at trends on the part. And in addition, there's a series of calculation glyphs, one actually being a full calculator that I could bring in multiple time histories, and in that calculator combine them to produce other outputs for comparison with my measured data. So within the DesignLife environment, you have a tremendous amount of signal processing available. What I'm going to do now is actually look at a capability that was introduced in version 9. It's called Lodz Reconstruction. And actually, it's nothing new inside of DesignLife. It was just taking existing DesignLife capability and putting it together as a worked example. And this particular worked example will allow us to bring in FE responses, and using the virtual strain gauge, we can take those responses and look at how each load or each mode in a model would appear on each of the strain gauges that are modeled inside of DesignLife. What I would get out then would be, in essence, almost a transfer matrix of, if I have loads in, these are the output strains, and we can take that matrix using the scripting glyph. The scripting glyph is nothing more than another glyph the user can bring in and, using Python or MATLAB, create his own internal glyph. This particular scripting glyph was created to go off and transform those responses. So now I have input strains describing what the loads would look like. And if we pair those up with measured strain histories, the output is a load history that would have had to be applied to the model to generate those strain histories. One thing to mention here, this is actually a worked example that came with version 9, worked example 20. It is using the scripting glyph, and the scripting glyph in this case is using Python. So in order to actually run this worked example, you need to have Python 2.6 installed as well as NumPy. The actual process that we're performing here is bringing in a set of finite element responses. And these responses would be either stresses due to unit loads for a variety of superimposed load cases, or they could be stresses for mode shapes if I'm looking at dynamics. But each one of those load cases or modes would be processed using virtual strain gauge, and it would generate for each one a set of strain gauge responses. What were the strain gauge levels from this particular input load or mode shape. If I assemble all those for each load case or mode in my model, again, I end up with a matrix that is the transform matrix, and I can actually pseudo-invert that, and if I take that new inverted matrix, multiply it with measured strains, the output would be the load histories that are necessary to generate those measured strains. I'm going to show you an example that I had put together, and this is looking at a wind turbine blade. And in this case, the blade was being physically tested for dynamics. So the blade was mounted, actuators on the blade to put it through an enforced motion. And the blade was actually instrumented with dozens of strain gauges. Again, the purpose of these gauges, in many cases, was looking at changes of response, trying to look for damage occurring in the blade. But they are measuring the response at multiple locations within the blade itself. So a finite element model was created of this blade structure, and that model had applied to it virtual strain gauges mimicking the actual gauges on the blade. So in here we have virtual strain gauges. In this case, they're all rosettes that were mounted on the internal spar as well as the leading edge of the blade. And these will mimic the response of the actual gauges. The FE model for this calculation was a dynamic model. So what we're looking to do is do modal superposition, use modal stresses along with modal coordinates to predict dynamic response. So the actual input into the virtual strain gauge was a modal analysis. And here we actually calculated the first 10 modes of the blade. I'm showing you the first 3. But what we get out of the modal analysis, besides being the natural frequency the mode is actuated at, as well as the display shape, we can get the stresses from those display shapes. These display shapes are going to be the degrees of freedom in a dynamic modal analysis downstream. And so what we're interested in is seeing from each one of these modal stresses their influence on the strain gauges, basically the output response to the strain gauges. So our input is these modal stresses. We bring it into the virtual strain gauge. We have virtual strain gauges applied at every one of the actual gauge locations. And in the load reconstruction process, again, we have multiple gauges, and you'll see this in just a bit, along with the modal stresses. They go into the virtual strain gauge, and it outputs a matrix that's going to be every row being one of the modes that were computed for this structure, and every column being the responses from a gauge for those modes. And this is just piped into the scripting glyph. The scripting glyph is taking that, doing a pseudo inversion on it, and now we have a matrix that says that this is the output loads for input strain. I take that and multiply that with our measured strain histories, and we can output the load histories. Let me actually show you that. I've brought back DesignLife, but this time I'm going to actually open a pre-existing process. So I'm going to go in and open up a process. That's the Lodz Reconstruction process. If I shrink this down a bit, you can see the overall process. We'll walk through this in more detail as I get going. And so I have inputs, again, for my finite element response, and again, these are the modal stresses from the modal analysis. You'll also notice that the strain gauges appeared immediately. And that's because when I had defined these gauges, I had specified a property on the gauge control panel that said save these gauges. So the gauges were saved out with the same model name as my final limit model. So anytime I open up that model, it sees that file and immediately imports those gauges. And so here you'll see that I have quite a few rosettes applied to this model that were automatically saved and remembered. And if I were to go in and get close to this, let's zoom up on one of these gauges here, we can see one of the rosettes applied to my structure. Again, this is a final model of the wind turbine blade, and I have a variety of fiberglass plies on this blade. You'll notice the color specification here is showing different ply configurations that are on this blade. And then the analysis for this was a modal analysis. And so if I go in and look at one of these modes, what we're looking at are the stresses from the first mode. One of the capabilities that was actually added at version 9 of DesignLife was the ability to go in and actually interrogate what the deflections are for a static or a mode shape. And so I'm just going to go in and show you. So the first mode for this model is nothing more than an out-of-plane first bending. Again, the second mode was in-plane bending. The third mode was a second order out-of-plane bending. And I have 10 modes described here. I'm going to go in and apply the measured strains. And so what we have here are 66 channels of measured strains. So that would basically be the 22 rosettes, 3 legs apiece for this. So that's my second input. That's the actual input, not to the first virtual strain gauge calculation, but to the scripting glyph. The virtual strain gauge is doing nothing more than looking at the individual load cases, the modes for this, and generating a response matrix. So I'm going to actually go off and run this. Well, actually, we'll go off, give you an idea of the load mapping. The quickest way to get those responses is just to ask for a time step load provider. So that's going to do nothing more than give me 10 snapshots of stress, each one being one of the modal stresses in the model. So that's what I've done here. And when we run this, its major output of the first virtual strain gauge is literally this matrix where each row is a mode shape, modes 1 through 10, and each column here is one of the strain gauges. So as I go down a column, I'm looking at a particular strain gauge's response to each one of the modes in the structure. Those were actually passed into the scripting glyph. The scripting glyph is taking that, doing a pseudo inversion. So basically it's turning it around. So now I have what the load responses are for each input strain. And I pair that up with these measured strain histories. Again, I have a measured history for each leg of every gauge in the model. And the output of that is, in this case, a set of responses for each mode. These are called modal coordinates. So these would be the scale factors for each mode in the model, then if I use these scale factors, multiply them by their individual modes, and sum up the responses, it would give me a structural stress history for this dynamic analysis. So these are the modal coordinates. And what we've actually done below is not really a check on the quality of the measured versus the predicted, but we're looking at the quality of the computation. We've taken the modal coordinates, passed them into another virtual strain gauge along with the modal stresses, and we've asked it to go in and output the strain histories for each lake. Along with that, we've plotted the input strain history. So what we actually have here is a computed strain history from the reconstructed modal coordinates, and our original input strain histories we brought in to the scripting glyph. And again, for correlation, we can go in and do things such as overlay these and look at every measured gauge versus the predicted gauges and look at the quality. Again, this isn't really looking at the ability to how accurate the loads were calculated, but it's looking at the numerical stability of the calculation. One of the powers of this, we have in the Finite model a full field description of modal stresses. We've gone through the Lodz Reconstruction, and we have physically created the modal coordinates. Combining these two together, I can predict a full field stress history. So what we're actually able to do here is take that reconstructed stress history, bring it into a StressLife or StrainLife fatigue glyph inside of DesignLife, and those two inputs will give me, for every location in the model, stresses or strain histories that I can do a full fatigue analysis on. What this means is I can go in and, having just a set of measure responses on the structure, I can recompute what the loads had to be coming in, and again, those could be static forces or could be these modal coordinates. And with those recomputed load histories along with the FE results, static or modal stresses, I can do a full model analysis in terms of fatigue, which is what we did in this particular case here. Again, what we're virtually doing here is turning our part into its own force transducer and using that to recompute the forces that would have been applied. Okay, so in summary, what we have been talking about today is, one, the virtual strain gauge that's inside DesignLife. And what that allows you to do is generate stress histories or strain histories from the virtual gauges on the FE model due to some loading response that I bring in, again, using the load provider inside of DesignLife, either time series, time step, constant, or duty cycle, and create histories that would mimic actual gauges on the physical part. With these virtual strains or stresses, I have the ability to go off and start looking at correlation of measured data versus FE predicted stress histories. And again, if I can't correlate stresses, then I'll never be able to correlate fatigue. But it gives me a way to go in and look at my model and convince myself that I have actually represented the stress histories, which means I've got the loads and boundary conditions correct, so I can go to the next stage and do fatigue. Finally, we looked at the virtual strain gauge in conjunction with the Lodz Reconstruction process flow that allows me to take in a set of unit loads or modes, generate a response matrix of each of those loads to virtual strain gauges in the part, and then I can go in and pair up that information with actual measured data at those strain gauge locations, and I can recompute or reconstruct what would have had to been either the modal coordinates or the loads for each of my unit loads on my part. And with this, again, I've turned my part into its own force transducer. Any analysis that I do that is using linear superposition, again, that could be modal dynamic or it could be linear static, can be used in this process. But the key is I am actually going in and superimposing stress states to do this, so they have to be linear combinations. But when I get done, I now have the required loads or modal coordinates that I could apply to my FE model and do a full field fatigue solution. Okay, with that, I guess I will pass this back to Amanda for the survey and open